You will be very surprised by what you are about to see in this video, because this underground railway tunnel has literally gone down in history as handmade, because we are talking about a structure excavated entirely by hand under nothing more than candlelight. In 1836, Isambard Kingdom Brunel proposed driving a railway tunnel through Box Hill in Wiltshire. This underground railway tunnel formed a route cutting through 1.83 miles of solid Bathstone limestone, separating the Great Western Railway's line between London and Bristol. No underground railway tunnel of this length had ever before been attempted in England, because there were fears that no ventilation system could possibly protect passengers. Doctors warned that the speeds of trains inside the tunnel would kill the human body, and even Brunel's own shareholders demanded that he reroute the line around the hill. Yet Brunel rejected all of this, and as a result, the underground railway tunnel was hand-excavated over 5 years by a workforce that peaked at 4,000 men, using candles, gunpowder and picks. 30 million bricks lined the tunnel interior, even where the solid rock required no support whatsoever. The tunnel opened in 1841. Today, 183 years later, high-speed trains pass through a railway tunnel built for 50-mile-per-hour steam locomotives that no longer exist, traveling at speeds exceeding 100 miles per hour, and this railway tunnel remains in active service. As you listen to this story, you will see a subscribe button beneath the video. Like the video and subscribe to the channel, because engineering built far beyond reasonable necessity often becomes, over time, the most necessary of all. The Great Western Railway faced a geographical problem with no elegant solution. The Cotswold Escarpment rose steeply between Chippenham and Bath, forming Box Hill, a limestone ridge 400 feet high, directly in the railway's path. Brunel had 3 options. He could route the line south, adding miles and gradients through difficult terrain. He could route it north, crossing the Thames Valley with expensive viaducts and earthworks, or he could drive straight through. The tunnel option was the shortest, most direct, and most expensive. The gradient through the tunnel would be 1 in 100, continuously descending from east to west, and the steepest sustained railway gradient yet proposed in England. Brunel chose the tunnel without hesitation. This decision alarmed everyone involved. The Great Western Railway Board had already accepted significant risk in financing Brunel's broad gauge system. The broad gauge required wider cuttings, wider tunnels, wider everything. Box Railway Tunnel needed to be 30 feet wide at the base of its arch, significantly larger than standard gauge tunnels of the period, and the additional excavation volume meant additional cost, so the board pressed for a narrower tunnel. Brunel refused to compromise. The tunnel was designed for the broad gauge, and the broad gauge would not be narrowed. Construction began in September 1836. The geology of Box Hill complicated every calculation. Bath limestone is not uniform. The rock varies from hard, dense freestone, the material used to build Bath's Georgian terraces, to softer, fractured layers intersected by fault lines and water-bearing strata. Brunel had limited geological information at the outset. Workers would discover the true nature of the rock only as they drove the tunnel forward. In some sections, the limestone was so strong that no support was required. Brunel lined it anyway. In other sections, groundwater seeped through fractured zones in volumes that exceeded pumping capacity. In one especially difficult stretch near the western portal, workers encountered a spring discharging hundreds of gallons per minute. The workings flooded repeatedly. Men pumped continuously. Progress stopped for weeks at a time. The excavation method combined gunpowder blasting with the manual removal of broken rock. Workers drilled holes into the tunnel face by hand, one man holding the drill while another struck it with a hammer, rotating the drill between blows to cut a circular hole. The work was loud, dusty, and dangerous. Each hole required hours of drilling. Gunpowder charges were packed in, fused, and fired. The blast shattered the limestone into fragments, which workers loaded into wooden wheelbarrows and hauled to shafts sunk vertically from the hilltop. 8 shafts were opened to intersect the tunnel alignment, allowing spoil removal and material delivery simultaneously from multiple points. The deepest shaft extended 300 feet from the surface to the tunnel floor. Winding engines at the surface continuously raised loaded skips and lowered empty ones. Even candle consumption alone illustrates the scale. 4,000 workers underground required constant illumination. Throughout construction, the tunnel consumed 1 ton of candles every week, more than 250 tons over 5 years. Each worker carried his own candle, fixing it to his hat, or wedging it into a crevice near the working face. The light was dim and localized. Men worked in near darkness, broken only by the small circles of individual flames. Air quality was poor. Gunpowder smoke hung in the tunnel for hours after each blast. Ventilation through the shafts was inadequate. The men worked in conditions that would shut a construction site down immediately today, and no matter how many precautions were taken, no one could escape the inevitable end. Approximately 30 workers died during construction. The causes reflected the dangers of the work: premature explosions when gunpowder ignited before workers had cleared the area, falls down shafts when winding equipment failed, rock falls from unstable tunnel crowns, drowning when floods overwhelmed escape routes. This fatality rate was considered acceptable for Victorian engineering projects of this scale. No compensation was paid to the families of the dead. The project continued. Brunel visited the works regularly, inspecting progress, adjusting the alignment, and solving problems created by unexpected geological conditions. The brick lining specification was Brunel's most conspicuous act of overbuilding. Where the limestone was sound, structural engineering required no lining at all. The rock could support itself indefinitely. Standard practice would have left such sections unlined, significantly reducing brick consumption and cost. Brunel lined every yard. The lining consisted of 30 million bricks distributed across the tunnel's 1.83-mile length, averaging nearly 3 feet of brickwork throughout. The bricks were made on site from local clay, fired in temporary kilns built along the tunnel route. Each brick was laid by hand in hydraulic lime mortar, capable of setting in damp conditions. The mortar joints were raked and pointed. The finished lining was smooth, regular, and massively excessive, even where the rock needed no assistance. Brunel's thinking extended beyond structural sufficiency. The underground railway tunnel would carry coal-burning steam locomotives. The exhaust gases, smoke and heat produced in an enclosed space nearly 2 miles long were unknown quantities in 1836. No engineer had experience with tunnels of this length operating at such speeds with such locomotives. Brunel could not calculate the thermal and atmospheric loads the lining would face. The brick envelope provided insulation against temperature fluctuations, a barrier against groundwater, and a smooth aerodynamic surface that reduced resistance. Where calculations failed, mass compensated. The portal design at both ends of the tunnel demonstrated another dimension of Brunel's approach. The western portal at Box Village was built as a classical stone facade, a dressed bathstone arch framed by pilasters and topped with a projecting cornice. The stonework was entirely decorative. The structural arch behind it carried the engineering load. The facade served no structural purpose, yet required skilled masons, quality stone, and careful craftsmanship. The eastern portal at Corsham received similar treatment. The effort and expense devoted to portals that passengers would only glimpse momentarily as their train entered or exited reveal something about Victorian engineering philosophy. Permanence and quality extended even to elements that were not strictly necessary. The railway tunnel opened in June 1841. The first public trains through Box required locomotive assistance for the eastbound journey against the 1 in 100 gradient. Westbound trains ran freely, controlled by brakes. The ventilation that critics predicted would suffocate passengers proved uncomfortable but survivable. The speeds doctors warned would be fatal proved exhilarating. The tunnel that shareholders claimed could not be built was complete. Total cost reached £247,000, significantly above the original estimate of £102,000. Part of the overrun was geological. Flooding on the western side required far more pumping and drainage than budgeted. Part reflected Brunel's insistence on lining every yard regardless of structural necessity. The broad gauge that made box tunnels so wide was eventually abolished. In 1892, the Great Western Railway converted its entire network to standard gauge. The broad gauge track was removed. Standard gauge track was laid inside the tunnel. The tunnel itself did not change. Its width, designed for 7-foot gauge trains, now provided considerable extra space for 4-foot 8.5-inch gauge traffic. The extra width that critics called extravagant in 1836 became an advantage when electrification and track improvements demanded wider clearances. The tunnel built for trains that no longer exist, adapted to serve trains its builder could never have imagined. Moreover, this railway tunnel survived both world wars without damage. During the Second World War, the western end of the tunnel was used to store railway rolling stock and ammunition. The constant temperature and humidity inside the limestone made it ideal for long-term storage. The brick lining Brunel installed even where rock needed no support proved vital for this purpose, providing a clean and durable surface throughout. After the war, rail traffic resumed and accelerated. The Intercity 125 trains introduced in 1976 began passing through Box Tunnel at speeds approaching 125 miles per hour. Speeds Brunel's locomotives could not have reached even on level track, let alone on a 1 in 100 gradient. Modern tunnel engineering offers an instructive comparison. The Channel Tunnel, completed in 1994, was designed for a defined operational lifespan of 120 years. It uses concrete segments, steel reinforcement, and modern waterproofing systems. The engineering is precise, with materials selected for exactly specified conditions. Box Tunnel, by contrast, was built with handmade bricks and hydraulic lime mortar, without any engineering specification for a defined lifespan. And this railway tunnel, criticized by so many, has now operated for 18 years and shows no sign of requiring fundamental renewal. The lining Brunel installed even where it was not structurally required has continued to absorb train vibration, thermal cycling, and groundwater pressure for 18 years without significant deterioration. Brunel died in 1859, 18 years after Box Tunnel opened. He never saw the broad gauge abolished. He never saw steam replaced first by diesel and then by electric traction. He never saw the speeds that his tunnel was large enough to accommodate, but his locomotives could not achieve. He built for a railway future he could not predict, using dimensions his shareholders called extravagant and his critics called impossible. Every train that passes through Box Tunnel at 100 miles per hour today validates the decision of a 29-year-old engineer in 1836 who refused to settle for minimum standards when permanence was achievable. The limestone that Brunel's men drilled and blasted by candlelight still forms the crown of Box Hill. The 30 million bricks they laid in hydraulic lime mortar still line the tunnel. The drainage system that consumed so much labor and money during construction still carries groundwater away from the bore. The portals that passengers glimpse briefly as their trains accelerate into daylight remain exactly as Brunel's masons built them. The tunnel does not ask to be noticed. It simply continues. Train after train, decade after decade, carrying loads its builders could never have imagined through rock they cut by hand, in darkness, by candlelight.